Alright, so this week we're going to start off by looking at 7.2. As I said, we're going to split that into 2 days. And 7.2 looks a little bit more at inverse trig functions, specifically like the domain and the range of them. So we'll talk a little about those. And then we'll talk also about transformations, like shifting them up and down, left and right, stretching them, and the transformations work exactly the same as everything we've studied all year. All right, so we'll look at those 2 things today. So first of all, let's just take a look at what an inverse function is in general. Visually, if you graph a function and you graph its inverse, they're mirror images of each other. But they're not mirror images over the x-axis or the y-axis. They're mirror images over the diagonal line y equals x. And let me show you how you get an inverse function. It's very, very simple. Let's start with a function that we're familiar with. Parabola, y equals x squared. Basic parabola. To get the inverse, what you do is you take your function and you switch the x's and the y's. That's how you create the inverse. And what I would like to do is graph that. But in order to graph it, I need to have y by itself. So can someone tell me, how would I get y by itself in this equation? What would I have to do on both sides? Yeah?
Take the square root.
Take the square root. So there's the inverse function of this function. And that should make sense if we just think about it. Inverse functions cancel out regular functions. What do square and square root do to each other? They cancel each other out. So I just want to show you this on the calculator so you can see it. Let's type in y equals x squared, but I only want to look at part of the parabola. I don't want to look at the whole thing because I'm only looking at the positive square root. You know, there's always 2 square roots, but I'm only going to look at the positive one. So I'm only going to look at the positive part of the parabola. Okay, so I'm just trying to keep the comparison accurate. So this is a piecewise function. We're only going to graph it for positive values of x. And I'm only going to do the square root for positive values of x as well. That I don't need to specify. The calculator will handle that automatic. And let me put in the line y equals x. So these should be mirror images of each other over the line y equals x. Let's do zoom 5. We don't do zoom 5 a lot, but I want to show you something. Zoom 5 makes the window proportional, so nothing is distorted. And let me zoom out even a little bit more. I don't know if this will be better or worse. Okay. So, if we take a look at that, go there. Can people see how, if you were to take, this was like a piece of paper, and you folded it on that black line, that this graph in blue would land exactly on top of that graph in red? People see that? That's what it means for a function to be an inverse. It would be a mirror image reflected right over that line. This part, just ignore, there's nothing I can do to get rid of that, but it should be there. Right, so that's squaring and square rooting. Well, what we're going to look at is trig functions and their inverse. Now, for a function to have an inverse, it has to pass a test. Does anybody remember the name of the test that a graph has to pass if it's a function? Yep.
The vertical line test?
Yes, the vertical line test. So the vertical line test tells you, just take a trig function. The vertical line test says if you take a vertical line and you put it, take a vertical line and put it anywhere in your graph, it would only hit the graph one time. Does that function that I drew on the board pass the vertical line test? Yeah, it would only hit, to make it a different color, it would only hit the green function one time. Vertical line test. Now, there's another test, and that's called the horizontal line test. The horizontal line test is used to tell if this graph right here would have an inverse that's a function. So vertical line test tells you if that is a function. Horizontal line test tells you if the inverse of that is a function. And the test works the same way. You have to be able to draw a horizontal line and it only hits the graph once. Does a horizontal line only hit that graph once? No. So what that means is this graph fails the horizontal line test, which means its inverse would not be a function. We don't want that. We want the inverse to be a function. How are we going to fix that? And we'll talk about what we can do. Okay. So for a function to have an inverse, it must pass the horizontal line test. And we just saw, this is the graph of sine, just done with a calculator. This graph fails the horizontal line test. But we know trig functions have inverses, right? There is such a thing as inverse sine, inverse cosine. So how are we going to do that if I'm telling you that this graph fails the horizontal line test? Well, maybe the entire graph fails the test, but maybe we can find a section that passes it. Like we can just zoom in on a small area and use that to find the inverse. Okay? And that's what we're going to do. Let's try, let me go like this. Let's take this, and let's just look at that window right about there. If I focus on that section, does that section of the sine graph pass the horizontal line test? No, I still haven't found a window that works. Well, you go like this. Drag this a little bit more to the right. Right about there, I think, is pretty good. How about that section? Does that section pass the horizontal line test?
Yes.
Yep. So we found a section that we can work with. Okay, we found a section that passes the horizontal line test, which means the inverse of this is a function, and that's what we want. We had to find a section that passed the horizontal line test. Now we have to kind of describe, well, what is that section? Let's see if we can figure out what it is. I think it was from here to here. It was this box right in here. So what we want to figure out is what's the left and what's the right edge of that box. Well, each mark that you see here, 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 and here, those are marking a quarter of a cycle. That's the 0, first quarter, second quarter, third quarter, and then the fourth quarter is when you're finished. That's a quarter, quarter, and quarter that way. Does anybody remember when you graph sine, what x value marks the first quarter? Like we have pi, 3 pi over 2, and 2 pi. Those mark the middle, third, and the end. 0 marks the beginning. Anybody remember the x value in radians? That marks your first quarter. Yeah,
Pi over 2.
pi over 2. So the right edge of that box is pi over 2. And what do you think the left edge of the box is, since it's exactly 1/4 to the left? Yeah?
Negative pi over 2.
Yep, negative pi over 2. So if we zoom in on the x values between negative pi over 2 and pi over 2, we've solved the horizontal line test problem. We found a section that passes it, which means we can now talk about inverse sine. Okay, so the solution to our problem, I already told you that, we're going to restrict the domain. Yes, technically sine goes on forever, left and right. But if we let it go on forever, we can't do inverse trig with that. So we're going to put a restriction on the domain. We're going to restrict the original x values to just be between negative pi over 2 and positive pi over 2. All right, let's write that down. So this is for the original sine. The domain, we're going to put restriction from negative to positive pi over 2, including. It's okay to include it. That's why we use the bracket. Now, what's the range? If you look inside that red box, what's the highest and what's the lowest that the sine function goes in that box? Or really anywhere. Yep.
1 and negative 1.
Yep, it's negative 1 to 1. That's the domain and the range for the graph of original sine. Now, I want to know the domain and the range for inverse sine, but it's going to be based on that. What did I do with the x and y values when I wanted to find the inverse of a function? I took my original, and what did I do with the x and the y values? Yeah? Yeah, I switched them. The x's became the y's, and the y's became the x's. So, if this is the domain and the range for regular sine, what do you think is going to happen to this domain and range when I talk about inverse? Yes, yeah?
It's going to switch.
They're going to switch. So for inverse sine, the inverse is where the x's become the y's and the y's become the x's. Another way of saying that, the domain becomes the range becomes the domain. So the domain will become negative 1 to 1, and the range will become negative pi over 2 to pi over 2. Now that we know that, we should be able to get a graph of inverse sine. We're not going to do any sketching by hand. Okay, any sketching we do is on the calculator. And if you have your calculator, you can do it, or you can just watch me. Can someone remind me, how do you do inverse sine? What do I have to press to get that to come up? Yeah, Chris?
Second sine.
Second sine x. Now, let's set the window. So the x's are negative 1 to 1. I want to go a little extra. Let's do negative 2 to 2. And or positive pi divided by 2, that's about 1.57. So let's go negative 2 to 2 on the range, and that'll give us a little extra. So negative 2 to 2, hit graph, and that is what inverse sine looks like. It has a definite starting and stopping point because we made the original graph have a starting and stopping point. If we didn't, this wave would just continue, and the problem is that would fail the vertical line test, and we didn't want that. So that's exactly what we just wrote down. for inverse sine, the domain is negative 1 to 1, and the range is negative pi over 2 to pi over 2. Now, let's do the same thing for inverse cosine. Let's look at regular cosine, see if it passes the horizontal line test, and if it doesn't, well, let's find a window where it does. All right, so let's put up the graph of regular cosine. And let me do zoom 7. Okay. Does that graph pass the horizontal line test? No. That fails the horizontal line test because it would hit more than once. So the goal, let's find a section that does pass. And there might be more than one section. We're going to go with the section that's most common, that everybody uses. So negative pi over 2 to pi over 2 worked great for sine. Let's try that here. Negative pi over 2 to pi over 2. Does it work here?
No.
No. Negative pi over 2 to pi over 2 fails the vertical line test. So we've got to find a section that works. Let's just try moving it to the right a little bit. How about right there? Yeah. No matter where you put this line, it would only hit the graph once. So we found a section that works, and we're going to base everything about inverse cosine on that section. Hey, anyone think they can tell me where's the left edge of that box? Chris?
0.
Yep. 0. And what's the right edge? Yep. Chris?
Pi.
Pi. It's at the second tick mark, which is the halfway point in a cycle. So, if you take cosine and you restrict the domain to be between 0 and pi, now you can talk about inverse cosine as a function. So, the domain is 0 to pi. What's that going to turn into when we talk about the inverse? 0 to pi is going to become the... Yep, exactly. The range is going to be 0 to pi. If you go back and look at the original cosine has a range of negative 1 to 1. Well, the range of the original turns into the domain of the inverse. Okay, so that's what we're going to deal with when we talk about inverse cosine. These domains and ranges are just starting points. If we do a transformation, like say we shift it, I don't know, say you shift it right 1 unit, well then this domain would be 0 to 2. If you shifted the left number to the right 1, and you shifted the other number right 1. So these can change, but they're your starting points. The last one we're going to look at is inverse tangent. We'll do the same thing. Let's look at the graph of tangent and see if it passes the horizontal line test. Okay, so here's tangent. Does tangent pass the horizontal line test? Well, Jake?
No.
No. Because if we draw a horizontal line, how many times would a horizontal line hit this graph?
A lot.
A lot. How many is a lot?
Six.
Oh, more than that. Yeah,
Infinite?
infinite. If you could zoom out forever, it would hit it infinitely many times. So we need to find a section that passes the horizontal line test. and then we'll base inverse tangent on that section. Okay, so let's make a box. And when I look for a section that passes, I have to find a section that's 2 tick marks wide. That's the rule. It's got to be 2 tick marks wide, which is basically pi units. Let's try what we did last time. Let's do 0 to pi. I know it's kind of hard, but just focus on what's in the box. If I put a horizontal line, would it ever hit the graph inside the box more than once? Is there ever a point where it hits more than once? Actually? No, technically it doesn't, but the only thing I don't like about what's inside the box is we've broken the graph into 2 pieces, so if there's a discontinuity because of the asymptote. It would be better if we could put it as one connected piece. So let's try a negative pi over 2 to pi over 2. How about that? Would that line ever hit the blue graph more than once inside the box? What do you think, Casey? No. No. Inside the box, it never hits more than once. So we found a section that works. What does this graph have in it, though, that sine and cosine don't? We've talked about these kind of things before. I think I said it a minute ago. Yeah? This has asymptotes. So, in fact, this left edge of the box is an asymptote. And so is the right edge of the box. So based on those being asymptotes, anybody think they can tell me how I would write the domain for tangent? What are we between? Be careful. Yeah?
Parentheses, negative pi over 2, to pi over 2, parentheses, close parentheses.
So the domain, this is for original tangent. Again, we really care about the inverse, but I'm just writing the original. Original tangent, we're going to restrict the domain to negative pi over 2 to pi over 2. Open interval, because of the asymptotes. What's the range? Yeah.
Negative infinity to infinity.
The range is negative infinity to infinity. And Matt, what's going to happen to this domain and range when I talk about inverse tangent? Yeah, it's going to flip. So when we have inverse tangent, the domain is going to be negative infinity to infinity, and the range is going to be negative pi over 2 to pi over 2. And that's exactly what I have right here. Range, negative pi over 2 to pi over 2. Domain, negative infinity to infinity. Now, just remind me again, what kind of asymptotes did we have in regular tangent? Yep.
Vertical.
Vertical. So what kind of asymptotes do you think we're going to have in inverse tangent? Sarah? Exactly. We're going to have horizontal asymptotes. They're still at exactly the same spots they were, pi over 2 and negative pi over 2. But instead of being verticals, now they're horizontals. All right, let's take a look at inverse tangent. So regular tangent went up and down forever. Inverse tangent is going to go left and right forever. Okay. So it looks a little different than inverse sine and cosine, so let's look at it. I'm going to set my window, well, since it goes left and right forever, negative 8 to 8, that's probably good enough. And then up and down, negative 4 to 4, I think that's fine. So there's your graph of inverse tangent. And hopefully you could kind of tell, if you put the line y equals x in, and I know there's more here than you need, but if you flipped it over that black line, this graph in blue should land exactly on top of that graph in here. The other blue ones, pretend that those aren't there. Any questions on that? Right, so that's your domain and range for the 3 inverse trig functions we're going to study. Does anybody need any of those again? Okay. So, we know that when you take a regular function and combine it with its inverse, it cancels itself out. Right? Here's an example. I took the squaring function, combined it with its inverse, which is square root, and what would you get if you simplified that? There? You just get 5. You get back exactly what you started with because you did something and then you undid it. Let's look at that with these trig functions. So I'm going to give you some different trig functions, and we're going to look at when they cancel out, because they don't always cancel out. It depends on what you plug in. If you take the inverse sine of the sine of something, the answer that you get back will be the something that you typed in, as long as the something is between 2 numbers. Let's look at an example with an actual number. Let's take the inverse sine of the sine of 0.8. When I hit enter, I get 0.8. These two things canceled each other out, and I got back exactly what it was when I typed in 0.8. Now, let me try a little different number. Let's try 1.8. Did I get back the same thing? That time I didn't. Okay. Let me try, for example, let's try 0.6. Well, that time I did. I got back the same thing. When you do or when you don't get back the same thing, it has to do with this inner function. And it has to do with the domain of it. Think about sine. What did we restrict the domain of sine to be? And if you can't think of the domain of sine, think of the range of the inverse. They're the same thing. So either the domain of sine or the range of inverse sine. Yeah?
Negative pi over 2, pi over 2.
Right, we restricted it to negative pi over 2 to pi over 2, which in decimal is about negative 1.57 to 1.57. That's why 1.8 didn't work. It wasn't between those two numbers. And now the formula right below it, it just switches the order you do it in. The sine of the inverse sine will cancel each other out. And what you get will be what you typed in, as long as you type in something between. Now look at that inside function. The way you figure it out is always ask yourself, what's the domain of the inside function? What's the domain of inverse sine? And if you can't think of the domain of the inverse, think of the range of the original. How high and low does original sine go? And that'll tell you the answer. Yep.
Negative 1 to 1.
Negative 1 to 1. So all these formulas, I've got 6 of these formulas, and they're all like this. They're all based on conditions involving the domain of the inner function. So let's look at these two. These are for cosine. Inverse cosine will cancel out regular cosine in formula 2a if you plug in a value between. Ask yourself what the domain of cosine is. the domain of cosine? Eli?
0, pi.
0 to pi. Why that domain? Because we found that if we focused on that window, it passed the horizontal line test. To be very clear, that is not the only window you could use, but it is the window that's most commonly used. All right, and what about the bottom one? If you do the cosine of the inverse cosine of x, you will get x. If you plug in a number between, what do you think? How about Bailey, what do you think?
-1 to...
Yeah, the domain of the inside function, -1 to 1. So you could try it. Take your calculator and type in cosine of inverse cosine of 0.63. If you type that in, you'll get back 0.63. Any question on that one? And the last two. Tangents. So formula 3, the first one, 3a, if you do the tangent of the inverse tangent of x, you will get back x. If, what do you think x, Abigail, what do you think x has to be between here? Sorry, what's that?
So I don't know, paying attention.
Not sure. Anyone help her out? What does x has to be between here? Yep, Ashley?
-pi/2 and pi/2.
So is it the same as that one right there? -pi/2 to pi/2?
Yeah.
That's
No, it's not the same as that. Yep, Chris?
-pi/2, but it's not including.
Right,
It's
it's
not equal to.
not including, because you have the asymptotes. So it's -pi/2 to pi/2, not including it. And what about the bottom formula? When will the tangent of the inverse tangent of x cancel itself out and give you back what you started with? Yeah?
Negative infinity to infinity?
So essentially, when is that?
Always.
Always. Formula 3b works all of the time, no matter what. So technically, there is no restriction on Formula 3b. So Zach, if I typed in the tangent of the inverse tangent of 34.6, what would I get?
Negative.
Not sure? It's not going to be negative. It's going to end up being positive in this case. Anyone help them out with? What would we get back based on Formula 3b? Jake?
34.6.
34.6. Because whenever you take the tangent of the inverse tangent, the answer that you get is whatever you typed in. And the condition is whatever you typed in. There is no condition. Could be anything. Okay. Any questions on that? All right, how about if I did the inverse tangent of the tangent of 2.5. What would happen there? Yeah?
Error?
I wouldn't get an error. But, yeah, Darcy?
2.5.
No, I wouldn't get 2.5. Yeah.
You would get a number that's not between negative pi over 2 or pi over 2.
No, I would get a number that's between negative pi over 2 and pi over 2. The answer that you're going to get back here always has to meet those conditions. If you plug in 2.5, this is the case where it will work. It will give you something, but it's not going to give you back the same thing you typed in. So if you type in inverse tangent of 2.5, you get negative 0.641. So I got an answer that meets these conditions. Now, what if I did this? The inverse tangent of the tangent of negative 0.641. What would I get if I did that? Chris?
Negative 641.
I would get negative 0.6.
0.641.
Yep. So if you do the inverse tangent of the tangent, negative 0.641, you do get back negative 0.641. So is there any question on when a trig function and its inverse cancel each other out? This is every combination you could have. Inverse on the inside, inverse on the outside. Okay. Now, let's look at transformations. We've looked at transformations now with at least 5 or 6 different kinds of functions. The transformations here are exactly the same as everything we've done all year. So, with that, can somebody remind me what A does to your function? Matt?
It shifts your that number either left or to the right.
Yep, so we'll talk more specifically in a minute, but let's just say that that's a horizontal shift for now. How about B? It's still inside, so it's going to have something in common with the transformation we just wrote down, but it's multiplication and not addition, so it's going to make another part of it different. Yep.
It's going to be a horizontal stretch.
So it's still horizontal, but it's a stretch. Okay, what about C? It's multiplication, so it's going to have something in common with B, but now it's on the outside. Yep.
Vertical stroke.
So it's a stretch, but it's vertical. And D, it's on the outside, so it'll have something in common with C, but it's plus, so it's also going to have something in common with A. Yeah? That's a vertical shift. If A is positive, which way would that move your graph? Yeah? Left. If it's negative, it would move it right. B, remember, the bigger you make B, the more compressed your graph gets. If you make B 10, that's a compression by 10. If you make B 1/3, that's a stretch by 3. So remember, B is the opposite. What if B is negative? What does that cause your graph to do? Yep.
It's a reflection.
Yep. Specifically, it's a horizontal reflection, which means it's a mirror image over the y-axis. C, if that was negative, that's a vertical reflection. With C and D, you don't do the opposite. If you make C a number like 10, that's a stretch by 10. If you make C 1/3, that's a stretch by 1/3, or you could really say compression. With D, if D is positive, which way would your graph move? Yep.
Up.
Up. And if it's negative?
Down.
Down. Okay. So what we're going to do is look at doing a transformation to an inverse trig function. Could be inverse sine, cosine, or tangent, doesn't matter. And we're going to look at how that changes the domain and the range. Now, think about domain first. Does your domain have to do with how far your graph goes horizontally or how far your graph goes vertically? Which one is domain? Yep.
Horizontal.
Horizontal. What are the two letters there that affect your graph horizontally? Jake?
A and B.
A and B. So if you were trying to find the new domain and you've done a transformation, domain is only affected by A and B. If you want to find the new range, all you have to focus on is C and D, because range is vertical, and C and D are the verticals. Does anyone remember what you call the thing that's inside the parentheses? That's the thing you're plugging into your function. Yep,
The argument?
that's called the argument. Yep, exactly. So, if you want to find the new domain of an inverse trig function, here's how you do it. What you're going to do is set up a compound inequality. We did those earlier. These are compound inequalities. They're conjunctions. That's another name. So set up a compound inequality with the argument in the middle and the original domain on the left and on the right. So your argument, let's just say your argument was 2x. Okay, b was 2. You do something like this. Put the original domain on the left and the right. Okay, where do you get the original domain from? Well, that's what we just went through. We made a chart of the original domain and range for every function. And to find your new domain, solve the inequality. In this particular problem, you'd have to divide everything by 2. So whatever the original domain was, now it's going to be half that. Everything's going to get divided by 2. So when I say solve, I mean get x alone in the middle. So domain, all you have to deal with is the argument. For range, you have to take into account 2 things. And the order you take them into account is important. With vertical stretches, with vertical transformations, do the stretch first, do the shift last. C, then D, alphabetical order. So let's say, I don't know, you had, I'm making up a range. Let's do -1 to 1. And let's say I wanted you to stretch that by a factor of 3. Stretch by 3. What would -1 to 1 turn into if you stretched it by a factor of 3? Yep.
-33.
Yeah, it would become -3 to 3. So to handle a vertical stretch or shrink, you just multiply each number by the stretch or the shrink, and that tells you your new range. Now, let's say I took that and did a shift up 1. What if you shifted -3 to 3 up 1? What would be your new low value, or your new y min, and your new y max, if they each went up 1? Sarah? -2 to what?
2.
I like the -2, that's good. But, yeah, it would be to 4. So that's how you find your new range. You just take into account a stretch, and then any shifting, just like that. Okay, and that's just an example. I just made that up. Okay, so let's find the domain and range of this. Inverse sine 2x. Jack, how many transformations are happening in that problem?
1.
Just one. So that means only one thing is changing. One of these stays the same. Anyone think they can tell me which one of those is not being affected at all? Eli?
Range.
Yeah, the range, because we're not doing anything vertical. So whatever my range is for the inverse sine, that's all I need to write down. Okay, what's my range for inverse sine? This is the basic range with nothing, don't alter it at all. Yep.
-1 to 1.
Let me think for a second.
Oh,
The
sorry,
domain-
-pi/2 to pi/2. I think would be the range.
Yeah, because the range of the inverse is the same as the domain of the original. And that's the -pi/2 to pi/2. So no change there. Now, find the new domain. Create a compound inequality with the argument in the middle. All right. Put the original domain on the left and the right. What's the domain of inverse sine? Jake?
-1 to 1.
-1 to 1. And Francesca, how am I going to solve that?
I have no idea.
Well, what are we trying to, what's our goal in solving it? We're trying to,
Solve any problem.
and when you solve an inequality, you're trying to, how do you know when you solved it? When you have what? Like, what about that tells you that it's not solved?
The 2.
The 2x, well, what do you want in the middle when you solve it?
Just that.
Just x. So how would you get just x in the middle?
You divide it,
Yeah, what would you divide by?
2 on each side.
Yeah, and in fact, not just each side, but the middle too. Divide by 2 everywhere. That cancels the 2 in the middle. And what's my new domain now? Let's write it as an interval.
-1/2 and then 1/2.
Yeah, -1/2 to 1/2, and it is a bracket because of the equal to means including. And that's it. That's your new domain, and your range stayed the same. Okay, let's try this one. Now, before we even do it, what is a 1/3 next to the x going to do to your graph? horizontal stretch by how much?
One-third.
We're mixing two ways of describing it. We could either describe it one way and say 1/3, or describe it using the word you said, which was stretch, but then we have to say it a little different. Chris?
Stretch by a factor of 3.
That's a stretch by a factor of 3. Yep, that's the simplest way to say it. So whatever happens here, something should be getting 3 times as big. And it's the domain, because the range is not being changed. It's the same as the last type of transformation. So range is still negative pi over 2 to pi over 2. And now think about your original domain. It's negative 1 to 1. And you're stretching it by a factor of 3. So Tyler, what would my domain be if I did that?
It would be -1 less than or equal to 1/x less than or equal to 1.
Okay, and now how would you get the x by itself?
Multiply it all by 3.
Yep, just multiply everything by 3. 3, 3. That's gone. And what's my new domain?
-3 to 3.
Negative 3 to 3. Which is exactly 3 times as big as the old domain. And that's exactly what should have happened. Okay, any questions on it? Alright, let's try, we've done some horizontal, let's try this one. Okay, Matt, what's the transformation there?
Vertical.
Yep, can you be more specific?
Vertical shift. Up 2.
Up 2, so that's a shift up 2. So Abigail, what is not affected by shifting something up 2? The domain. So this time we can keep the domain the same. And Jack, what's the domain for inverse sine?
-1, 1.
Yep, negative 1 to 1. And now we're taking the range and we're shifting it up 2. Casey, what's my range for inverse sine? Negative pi over 2 to pi over 2, and you're shifting it up 2. Yeah, it's not really a nice way to write this answer. So all we're really going to do is this. Negative pi over 2, shift up 2, positive pi over 2, shift up 2. If you want to round it off to a decimal, you can. That's fine. But I'm just going to leave it like that. Questions on? All right, how about, all right, let's do inverse cosine. We haven't done that yet. Eli, what kind of transformation do I have there?
Vertical stretch.
Yep. So, Francesca, what is not affected by a vertical stretch? So your choices are domain or range?
Domain.
You sure?
No, it's range.
No, you were right.
Okay.
So when you stretch something up and down, it doesn't do anything to the domain. Like if you take something and stretch it taller, that changes the range. So the domain here is not affected by the vertical stretch. Chris, what's my domain for inverse cosine.
Negative 1 to 1.
Yep, negative 1 to 1. Now the range is going to be multiplied by 5. Ethan, what's my range, original range for inverse cosine?
0 to 5.
Yeah, 0 to pi. And you're stretching that 5 times as big. So it's going to be 0 to 5 pi. And that's it. So any questions on finding domain and range of an inverse trigonometry? Now, with inverse tangent, what could you never change? It would have the same answer every time. Either the domain or the range. Which one of those would never change no matter what transformation you did? Yeah?
The range,
Why?
because it was negative infinity to infinity.
For inverse tangent, let's check.
The domain.
It's the domain. So no matter what transformations you ever do to inverse tangent, you cannot change the domain. It goes left and right forever. If you shift it right 3, still goes left and right forever. So you can't change the domain of inverse tangent. Range, yes. Make sure if you're dealing with inverse tangent, you always use parentheses. The only time you can use the brackets are inverse cosine and inverse sine. Okay, so take a look at this format, okay, how we write an inverse trig function. And I'm going to put something up that's not quite that format. And I want you to tell me what I would have to do to make it that format. What I want to know here are the transformations that are happening, but there's something I kind of need to do first. Does anybody see what we need to do first to make this so I can kind of see all? I can't really see the 2 of the letters easily. I don't know what they are. Yep.
You have to distribute the 1/4.
Yeah, I really want it without parentheses. You're not supposed to have parentheses on the inside of the parentheses that are already there. So if we distribute it out, we have 1/4 x plus 2. Now I can see the A, the B, the C, and the D. All right, so how about Zach? Can you tell me how many transformations are happening there?
3, 4,
Oh, 4? You tell me what numbers are going to cause transformations.
plus B,
That's gone. We replaced that with what's above.
oh, right. So the number 5,
Okay.
and the 3 times the sine.
Yep.
So there's 2. Oh no, there's still 4, because it's still the plus 2 and
The plus 2
the 1/4 times.
and the 1/4. Yep. So there's 4 things happening. They don't care about domain and range. They just want you to tell the 4 things that are happening. And we do have to write them in the correct order. Okay. So Ashley, what number do I focus on first?
The 2.
Yep. And Bailey, what's the 2 going to do?
Move it to left 2.
It's going to shift it, yeah, left 2. So let's just do shift left 2. Okay, perfect. Took care of the 2. Jake, what's the next number we focus on?
That'll be the 1/4 x.
Yep, 1/4 x. And Sarah, can you tell me what the 1/4 x is going to do?
It's a horizontal stretch by 4.
Yes, horizontal stretch by 4. Perfect. All right, Matt, what's the next number we look at?
Well, the vertical shift.
No, something before that. The vertical shift is the D in the thing. We still have a C to look at.
Okay, so then the vertical stretch.
Yep, the vertical stretch. And Abigail, how would you describe the vertical stretch here? Yep. So vertical stretch by a factor of 3. Factor of 3. And Jack, what would be my last transformation?
Vertical shift down by.
Perfect. Shift down 5. Any questions on identifying the transformations? Alright, and last thing. So the last thing, kind of a review. We did this in 6.5, just practicing typing in an inverse trig function and getting the answer. Now remember, anytime you do inverse trig, you're solving for an angle. That's what inverse trig is used to do, is to find an angle. So you have to pay attention to what the directions say. Do they want it in radians or do they want it in degrees? These directions don't say. So I'm going to just pick degrees. Okay, I'll do it in degrees. Now for this one, I want the exact answer. Remember, the way you find an exact answer, if it's possible, is you have to do it in degrees first. So if I'm in radians, if I type in inverse sine of 0.5, and I ask you for the exact answer to this problem, and let's say I did ask for it in radians, and you tell me 0.5236, that's a decimal, right? That's not the exact answer. The only way you can get the exact answer, if it even exists, try it in degrees first and see what you get. If there's an exact answer, then this problem has to be a multiple of 30 or 45. That's the only way we're going to be able to figure it out. And it's exactly 30. So 30 degrees. Now, does anybody remember what you multiply by to change that to radians? Yep.
Isn't it pi over 180?
Yep, exactly. Pi over 180. The degrees would cancel. And how many times does 30 go into a 180? Check. 6. That's how you get the exact answer. As a decimal, it was 0.523598, so on. Type in pi over 6 and see what you get. It's exactly what you had before. But now you know the exact answer and not a decimal. The calculator will never give you pi over 6. It'll give you 0.5235. Okay. You have to do it in degrees and then convert it by hand. That's the only way to do it. These other ones you couldn't do as an exact answer. So let's just type it in. Inverse cosine of negative 0.7 gives me 134.43 degrees. Okay, so I chose to do this one in degrees. I'm just trying to practice both, so you see both. Inverse tangent of 4.3. Before I hit enter, can someone remind me, what's the domain of inverse tangent? Think about how far left and right the graph goes. Yep.
Negative 10.
Yeah, so that's going to work fine. I'll get an answer, 76.91. That's fine. inverse sine of 1.2. What's the domain of inverse sine? Chris?
Negative 1 to 1.
It's only negative 1 to 1. So that's undefined. You can't do that. And if you try it, it pretty much tells you exactly what's wrong. It says that there's an error because you tried to plug in a number not in the domain. You can't do that. It's like taking the square root of a negative. If you're not using imaginaries, you can't do it. So this has no solution. Any questions on that? All right. So that finishes up the first part of 7.2. We still got about 11 or 12 minutes. So if you have any questions, anything you want to touch base with me about, now is perfect. You got a little bit of time. Okay, so that's the homework on 394. The 1 through 9, that's just odd. And then everything else is just what I wrote. Right, and we'll take a look at that tomorrow.